Here we're going to look at another classic optimization problem in which you're trying to optimize the volume of a box that you're going to create by cutting out little squares in the corners of a piece of cardboard you have. So the first thing we want to do is read the problem and then model it correctly. So this says a 16-inch by 30-inch piece of cardboard is to be made into an open-top box by cutting squares of length x from each corner and then folding. Find the dimensions of the square that should be cut in order to maximize the volume. Okay, so first of all, hopefully you understand that this can be done. I think the first time I taught this, I remember some of my students didn't even know how this could be done, so maybe I'll take a second and make a few comments about that. But the idea is you've got this 16-inch by 30-inch piece of cardboard, and what you're going to do is you're going to cut out some squares. You're going to cut out some squares into the corners. And when you do that, it allows you to actually create an open top box. So if you cut out those corners, what you'd be left with would be this. Something that looks like this. So it would just be, actually what I'll do is I'll just erase I'll just sort of erase those corners. So if I take out those corners, what you end up getting is something that looks like this. All right, and if you fold along these, those creases right there and fold up, what you can end up doing is you can make this look like, a box that looks. Let's see how my intro to painting skills came in, or intro to drawing rather, in college. You could make something that looks like this, where this here would be, that here would correspond to the dimensions of that square that you cut out. All right, so hopefully you're convinced that that can be done. So the first thing to do is to figure out what would the volume of this box be in terms of x. So we've removed, we know that we've removed these corners here. So I know that this here should be x, right? So this that's x as is this, and actually this is as well. So then we have to ask ourselves, well, what would this length right here be? So hopefully after a few seconds of thought, you would say, okay, well, it used to be 30, and then I removed two x's, so it's 30 minus the two x's. And this side over here, well, that's the 16 except for the two x's, so it would be 16 minus 2x. And so now we can see that the actual volume of this box is going to be length times width times height. So maybe this side here would be called the, maybe this side here would be the 16 minus 2x, and maybe this guy here would be the 30 minus 2x, and that would produce your volume. All right, so this picture was helpful. So this is all part of the modeling step. So we want our function. So our volume function is just going to be the length of the box times the width times the height. All right, so before we go any further, the point is to find the dimensions of the square that's going to give the maximum volume. So we're going to want to find this maximum volume, or at least where it occurs. But before we do that, let's just talk about the domain of this function, because this volume function is going to end up being a polynomial, which has domains negative infinity to infinity. However, in this case, we don't want to consider all x values. A negative x value wouldn't make sense in this problem. So let's just have a discussion about the domain of this function so we'll know what our endpoints are. Well, first of all, I'm obviously going to cut out something from this box, right? I mean, x can't be 0 or negative, so x needs to be bigger than 0. So I'm not looking at negative values. But we could probably do better than that, because not only that, the sides, 30 minus 2x, for instance, that has to be a positive number. Right, that's a side length, so that needs to be that needs to have be a positive value. So if you solve this little inequality, that tells you that 30 needs to be bigger than 2x, which means that 15 needs to be bigger than x. Okay, so now we know x has to be in between 0 and 15. However, the same needs to be true of our other side, the other side of our box. 16 minus 2x, that side length, needs to be positive. And that means that 16 is bigger than 2x, which means if you divide by 2, 8 is bigger than x. So that means if you put these together, the real restrictions are that x needs to be bigger than 0, and it needs to be less than 8. So our domain would be 0 to 8. Now I'm not including those endpoints, right? I didn't put hard brackets, so we really don't have to check endpoints in this problem. Because if you check endpoints, or if you consider endpoints, you're probably not even going to have a box at all, right? If x is 0, there's no box, and if x is 8, there's no box. So that's good. We're just going to consider critical points. Okay, so we've got the modeling step down. Now what we're going to need to do is solve. So let's solve. We're going to want to take the derivative of this function. Right now it's the product of 3 functions. So I kind of want to multiply it out so I can use the power rule. So if you multiply all those out, you end up getting v of x equals, so I'm going to let you multiply that out and just confirm this. You end up getting that. So there's our volume function. If we want to find critical points, we're going to take its derivative. So that gives me 12x squared minus 184x plus 480. Alright, so critical points are going to occur where the derivative is either undefined or 0. This derivative is defined everywhere, so we'll just set it equal to 0. And one thing you may notice is that there's probably a common factor in the 12, the 184, and the 480. And after a little thought, I think you'll see that the common factor is a 4. So this is just 4 times 3x squared minus 46x plus 120. And that, I think, factors. That factors into 3x minus 10 and x minus 12. All right, and so then we've got, kind of move this over here. So now I know that x equals 10/3. I know x equals 10/3 and x equals 12. Now 12 can be eliminated because it's not inside our domain. Our domain is 0 to 12. So that means we're only considering 10/3. Alright, so that's most likely our answer. But what we'll probably need to do is just to make sure that we're being thorough, we're going to want to convince ourselves and the person reading this problem that we actually found something that corresponds to a max. So I'm going to do a v prime number line. It's going to go from 0 to 8. And I'm going to put 10/3 on there. And I'll plug in a number like 1 into my derivative, and I guess I'll plug it into this version here. If you plug in 1 into the derivative, you get 12 minus 184, which is a negative number, plus 480, which is definitely going to make that a positive number. So the derivative is positive there. And then if you plug in a number like, let's say 5, here I think I'll plug into the bottom, the factored version. That's going to be 4 times 3 times 5 minus 10, that's positive, times 5 minus 12, which is negative, so that's a negative. So I know I found a max. The other option, if you're interested, you could also use the second derivative test, right? You could take the second derivative and then plug in 10/3, and if it's a negative number, you know you found a max, and if it's positive, you found a min. So we don't have to do that, but that's just something, just a remark to note. All right, and so we're pretty much there. We know we found a max, and therefore we can interpret this problem by saying that, now remember, 10/3 is x, so that corresponds in this problem to the dimensions of the square we cut out. So that means that the square should be 10/3, and the units are inches, by 10/3 inches. And there's our final answer. So you can use a graph or a calculator or Desmos or something to help as you're doing this problem. Again, just make sure that the process is showing the person who's looking at this problem that you're using calculus and not just your calculator. So on the next page, I'm just going to show you the graph of our volume function, and you'll see that we've got that 10/3 is our x, and it also gives the y value, which would be the maximum volume itself. All right, so here's the graph of the volume function, and you can see that 3 1/3 or 10/3 is indeed the x value corresponding to our max, and if it actually asked for the maximum volume, you would plug 10/3 into your volume function and you would say 725.9 cubic inches.